Welcome to Efiwe, excellence without stress.
Welcome guys to Efiwe, excellence without stress. And today we are going to be considering something quite interesting. But before we get into that, everything that you can see and touch is matter. But what of some things like air which you can't see, neither can you touch? Will you still consider that matter? Join me as we go on a study to understand the particulate nature of matter. The first thing we are going to talk about is, what is matter? Matter is simply anything that has mass and can occupy space. And to understand the concept of matter, one must be able to know the following things. First off, you must understand the states of matter. Then secondly, you need to understand the different particles of matter. And finally, you should be able to know the forms of matter. What then are the states of matter? The state of matter simply describes the physical condition in which matter can exist. And there are three major states of matter. There is a fourth one though, but that fourth one is not so prevalent. The three major states of matter include solid, liquid, and gases. The fourth one is called plasma. As I said, it is not so prevalent. Moving ahead, what is a solid? A solid is simply a state of matter in which constituent particles vibrate around a mean position. And the implication of this statement is that every particle vibrates. Yes, we know that. But in the case of a solid, its vibration is more or less regulated to a very small point or to a very small distance. Because of this, you will notice that solid particles will be held together. The major reason we have that solids cannot vibrate beyond a particular region is because it has the strongest intermolecular force between them, as you can see amongst the properties. The second property of a solid is that it has definite shape. It also has definite volume. I'm talking about shape. If you look at your head and your head has a shape, it means that you are definitely a solid, or your head basically is a solid. As we said, the third property is that, okay, let's take that joke again. The second property of a solid is that it has definite shape. So which means if your head has a shape, your head is a solid. It also has definite volume, and then it has the least compressibility and thermal expansion. When you talk about compressibility, you will notice that because it has the shortest distance between atoms, the level of compressing it or bringing it together would actually be the least compared to that of liquids and that of gases. We go to the next state of matter, and that is liquid. A liquid is a nearly incompressible fluid that takes the shape of its container but retains a nearly constant volume. So yes, it is a fluid just as a gas. Liquid and gases are fluids, they flow. However, in the case of a liquid, it is nearly incompressible and also has a constant volume. The properties of liquid include, it has an intermediate intermolecular force, meaning that the force of attraction between molecules is not as strong as that of the solids. Neither is it as weak as that of the gases. Second thing is that a liquid does not have a shape, but then it takes the shape of its container. So if we consider, for instance, your toothpaste, which doesn't necessarily have a shape but takes the shape of its container, we could say that it is a liquid. However, in some cases you can refer to it as a semi-solid. The third property is that it has a definite volume, which means if you have 20 liters of a liquid, it remains 20 liters and doesn't change. And then finally, it is relatively incompressible. It is not so compressible because the distance between the particles of a liquid are relatively close, though not as close as that of a solid. Then we go to a gas. A gas is a state of matter in which the constituent particles are in constant random motion. So we have emphasis here. Constituent particles are in constant random motion. One of the things that enables this gas to be in constant random motion is the fact that ideal gases are supposed to have perfectly elastic collision. We'll talk about these properties when we get into gas laws. But then, for now, the general properties of gas include, it has the weakest intermolecular force, and that's why it's free to move around. Secondly is that it has no definite shape. It also has no definite volume, and then it is compressible. So you have that gases can actually be reduced, the volumes of gases can actually change or be compressed into smaller containers. Then we go to the last one, plasma. Plasma is basically ionized gas or a gaseous state that contains an appreciable amount of an electric charge or charges. So the emphasis here is, if you happen to ionize a gas, for instance, by making it to lose its electrons, the electrons combined with the ions would eventually lead to a particular state of matter called plasma. And that's that generally about plasma. Moving on, we'll now talk about the particles of matter. There are 3 particles of matter, which include atoms, molecules, and ions. And when you describe the particles of matter, you are looking at the constituting or building blocks of every existing substance. So, what is an atom? An atom is the smallest part of an element, and it is generally made up of 2 parts, the nucleus and the orbit. The nucleus is the central and houses the proton and neutrons, while the orbit basically is a space that surrounds the nucleus, and that is where electrons are found. The particles of atoms include the protons, the neutrons, and the electrons. The protons are positively charged particles, and they are found inside the nucleus of an element. Mind you that the number of protons determines the properties of that element. So when you are looking at a particular element like oxygen and it has 8 protons, what makes oxygen oxygen is that it has 8 protons. If I have a random element X and I tell you that it has 9 protons, because I know that the 9 protons is supposed to be for fluorine, that element is fluorine. So mind you that the number of protons is basically what determines the properties of that element. Now, the periodic law states that the properties of elements is a periodic function of its atomic number, and that atomic number is simply the number of protons. So anytime you are looking at the property of a particular element, it is simply dependent on its atomic number. Then finally, then we go to the next particle, which is the neutrons. The neutron is a particle of the nucleus which contributes to the atomic mass but has no charge. So it is neutral, however, it is a major part of the mass of an atom. Proton and neutrons are collectively called nucleons. It actually makes sense because, they are both found in the nucleus, so they are like nucleons. Okay, moving ahead. We are now going to talk about atomic mass and isotopy. Talking about atomic mass, it's important to note that atomic mass is simply the sum of protons and neutrons. And the implication is that if you have 5 protons and you have 5 neutrons, your atomic mass will simply be expressed as 10. Why is that? It is simply because when you are asked to find the atomic mass, it is going to be given as number of protons plus number of neutrons. I would like to say this. Every symbol denotes or gives 4 pieces of information. At the subscript towards the left, you have the atomic number, which will tell you the number of protons. Then you have the atomic mass as a superscript towards the left, which is protons plus neutrons. Then you have your charge. Your effective charge is the sum of the charge of the electrons plus that of the charge of the protons. And then finally you have atomicity. Atomicity simply describes the number of atoms in a molecule of an element. So back to what we were talking about. If you have the atomic mass is proton plus neutron, neutrons will be equals atomic mass minus protons. So if I have that chlorine is represented by 37 and 17, and I ask what is the number of neutrons here, the number of neutrons will be equals atomic mass, which is 37, minus the number of protons, which is given by the atomic number 17, and that will be 20. I presume that this was well understood. So we move ahead. So the next thing we are going to talk about is the fact that different atoms of the same element could have varying number of neutrons. And a variation in this number of neutrons is basically what leads to a phenomenon known as isotopy, where they would now have different atomic masses. So if we are to define isotopy, isotopy is simply a phenomenon in which different atoms of the same element have the same atomic numbers but different atomic masses. As I said, the variance in the atomic masses is caused by a difference in the number of neutrons. So if we are now asked to find an isotopic relative atomic mass, it is expressed mathematically dependent on the type of isotopic abundance given. But before we get to that, to express what we discussed about isotopy, you will notice that we have chlorine 35, 17, and we also have chlorine 37, 17. If we are to pick the element or the atom we are going to use, both of them are the same elements, but then are we going to use the atomic mass of 35 or the atomic mass of 37? We will notice that choosing either of the two would not make sense. So what do? We find an average value. That average value is what we refer to as the relative atomic mass. Now, This relative atomic mass is the isotopic relative atomic mass and is dependent on the isotopic abundance. Hence, if you have the isotopic abundance as percentage, you will have that the relative atomic mass will be given as atomic mass 1 times percentage 1 plus atomic mass 2 times percentage 2 all over 100, where AM1 is atomic mass 1, percentage 1 is P1 is percentage 1, AM2 is atomic mass 2, P2 is percentage 2, and RAM, as we know, is the isotopic relative atomic mass. To help us understand this, let's solve this question. So the question says chlorine consisting of 2 isotopes of mass numbers 35 and 37. So I like writing out my variables or my parameters basically. So we have that chlorine, we have the first chlorine, it has 35 as the atomic mass or mass number, and the second one is 37. So mind you, atomic mass is the same thing as mass number. So we go on, having written that, we now have that they have a relative, this should be relative atomic mass of 35.5. So let's be putting that down. The relative atomic mass of 35.5, relative atomic mass is equals 35.5. So what then is our question? So the question now says the relative abundance of the isotopes of mass number 37 is dash. When you talk about the relative abundance, in this case it is in percentage. So we are going to be looking at the percentage abundance. So how do we find the percentage? Very simple. Outlining our parameters, the initial atomic mass is equals that of chlorine 35, so 35, and the initial percentage was not given, so let's call it X. The next atomic mass is 37 and its percentage was not given, so let's call it Y. However, we know that the sum of percentage X plus Y is equals 100, which means if we are looking for Y, Y will be equivalent to 100 minus X. So in place of Y, we are going to have here 100 minus X. So let's get to solve. The formula for finding relative atomic mass when you have percentage is given as atomic mass 1 times percentage 1 plus atomic mass 2 times percentage 2, all divided by 100. With this said, let's get to solve. So we have that the relative atomic mass in this question is given as 35.5. And then it is equals, the atomic mass 1 is 35. Then the first percentage is X because we don't know it. It wasn't given. The second atomic mass is 37. And its percentage is Y, which is equivalent to 100 minus X. So moving ahead, dividing by 100, if we cross multiply, 35.5 times 100 would give us 3550, which is going to be equals 35X plus 3700 minus 37X. Taking our like terms, minus 37x will become plus 37x crossing over, while this will become minus 35x equals 3700 minus 3550. If this is to occur, we are now going to have that 2x would be equals 150, and dividing through by the coefficient of x, we'll find out that x is 75. Now note, x is the percentage for 35 and that is 75%. But then the question says, let's look at what the question says. The question says, what is the isotopic or relative abundance of the isotope mass of 37? We know that that of 35 is X, which is 75. So let's now find that of 37. If 37's percentage is Y equals 100 minus X, we'll have that this will become 100 minus 75, and our answer will be 25. So if you look at the options, our answer is going to be option B. I hope that was well understood. Moving ahead, isotopic abundance can also be expressed in ratio, and when it is given in ratio, you will find out that the formula will now be atomic mass 1 times ratio 1 plus atomic mass 2 times ratio 2 divided by the sum of ratios R1 plus R2. If they are up to 3, I hope you know you are going to do R1 plus R2 plus R3, so take note of that. So with that said, an element X has 2 isotopes, X2010 and X2210, present in the ratio of 1:3. So let's start writing out our parameters. Take this out. So we have that the first atomic mass is X2010, which is 20, and we'll find out that because you have a ratio of 1:3, the ratio there would imply that this particular first element will have 1, while the second atom of the same element will have 3. So with that said, the first so we'll have ratio 1 would be 1, and then for atomic mass 2, which is 22, ratio 2 would be 3. So let's get to solve. If we're going to solve this, the relative atomic mass when you have ratio is atomic mass 1 times ratio 1 plus atomic mass 2 times ratio 2, all divided by R1 plus R2. So the relative atomic mass, which is what we are asked to find, would now be given as the atomic mass 1, which is 20 times ratio 1, which is 1, plus the atomic mass 2, which is 22 times ratio 2, which is 3, all divided by 1 plus 3. So if this is the case, this is now going to give us, let's take this up, it's going to give us RAM equals 20 plus 22 times 3 is 66 divided by 4, and the RAM is going to be equals 86 divided by 4. Therefore the relative atomic mass is going to be equals 21.5. So if we look at that, you will notice that if we bring up our options, it is going to be option C. With this said, I hope this was fully understood. Now we are going to discuss molecules. A molecule is the smallest part of a substance that can exist on its own in nature and still possess the properties of this substance. This is actually what differentiates an atom from a molecule. Even though the two of them have similarity of being the smallest parts, a molecule is the smallest part of a substance, which means that it could be the smallest part of an element or the smallest part of a compound. However, an atom is basically the smallest part of an element. So have that in mind. Molecule is the smallest part of a substance, which means elements or compounds, but atoms is just for elements. The second differentiating factor is that once you are considering a molecule, it can exist on its own in nature. But not all atoms can stand alone. For instance, hydrogen as an atom cannot exist on its own. For it to exist, it will need to pair with another atom for it to be able to stand in nature. Hence, molecules can stand alone in nature, while atoms, not all of them, can exist alone in nature. With that said, we move on to the next thing. The number of atoms in a molecule is what we refer to as atomicity. So as I said, for some atoms to stand alone, they will need to bond with other atoms. And the number of atoms that are bound together inside one molecule is what we refer to as atomicity. Now we go to the next one, which is atomicity trends. All gaseous elements exist as diatomic molecules, except noble gases and ozone. So once you are considering a gaseous element, the gaseous elements that exist, there are 11 of them, and out of the 11 of them, 5 of which are your normal gases: hydrogen, nitrogen, oxygen, fluorine, chlorine. Hydrogen cannot stand as an atom alone. This is an atom of hydrogen, but for it to exist in nature, it has to join with another atom to form a molecule of hydrogen. So just have that in mind, that once you are considering a molecule of hydrogen, there are 2 atoms in one molecule, but hydrogen atom is just one. Nitrogen, oxygen, fluorine, and chlorine also applies to this. However, your noble gases are not diatomic, and obviously ozone is O3, so it is also not diatomic. Moving ahead, we go to the next one. The next property, or the next atomicity trend, is that all halogens exist as diatomic molecules. Your halogens are your group 7 elements, which include fluorine, chlorine, bromine, iodine, and astatine. So just take note of that once you are representing them, whether they are solids, liquids, or gases. For instance, your fluorine is a gas, your chlorine is a gas, your bromine is a liquid. So once it is a halogen, this one is a solid. Once it is a halogen, you represent it as diatomic. Then finally, metals, noble gases, and most solid metals are represented as monatomic. So sodium, for instance, is just one atom. Noble gas neon is just one atom, and carbon, which is a solid non-metal, is just one atom. So moving ahead, we go into the next part. What then is an ion? An ion or ions are basically charged particles that are formed by gain or loss of electrons. There are 2 types of ions. Number 1 is cation, which is a positive ion formed by loss of electron, and then number 2 is anion, which is a negative ion formed by gain of electron. There's this simple trick I use to remember or differentiate between the two and avoid confusing myself. When I look at my spelling of cation, I spell my cation with my T looking like a plus, and this plus T indicates positive. So I tell myself that this is Ka, positive ion. On the other hand, when I spell anion as an acronym, which means A. N stands for negative ion. So you could use that too, it could help you. positive ion, and this is a negative ion. So with that said, we move on to the next section of this particular study, and that is the forms of matter. Elements are basically one of the forms of matter, as well as compounds and mixtures. And when you consider an element is simply a substance that cannot be broken down into any simpler form by physical or chemical processes. So the implication is that if you consider water is definitely not an element, because I can break water to give hydrogen and oxygen. But then, can I break down hydrogen to give me any other thing? No. So hydrogen is an element. Oxygen cannot also be broken down to give me any other thing. So oxygen is an element. Moving ahead to the next one, you will find out that the next form of matter is compound. And a compound is a combination of two or more substances which are chemically bound together. On the other hand, you find out that a mixture is also a combination of two or more substances, but then they are not chemically bound together. So let's consider the differences between compounds and mixtures. First off is that compounds are chemically bound together, but then mixtures are not chemically bound together. The second difference is that components of compounds cannot be physically separated, but in the case of your mixtures, the components of your mixtures can be physically separated. So the implication is that if you are going to separate a compound, for instance, it is definitely going to be leading to formation of a new substance, which describes chemical process. Like when I want to break down this ammonia to give nitrogen and hydrogen, you will notice that it would require a breaking of a chemical bond, and basically that is a chemical process. But in the case of maybe separating the constituents of air, nitrogen, oxygen, I simply use fractional distillation, which is a physical process. So have that in mind, that when you want to separate your compounds, you would have to use a chemical process, but for your mixtures, they can be separated by a physical process. The ratio of components of a compound is fixed. Anytime you are considering a compound, like in the case of water, the ratio of hydrogen is always going to be 2:1 for it to be called water. But then if it is just a mixture, for instance, you will notice that your egusi soup, which is a mixture, sometimes you will use 1 cup of egusi and 2 cubes of maggi. Sometimes you will use a cup of oil and another different quantity. So you have varying ratios when you want to combine mixtures. But for a compound, the ratio of their components are always fixed. The boiling point and melting point are also constant for a particular compound, while in the case of the mixtures, it could vary. And then finally, energy is given out to prepare a compound through chemical bonding, but then there is little or no energy transfer when you are combining mixtures. With this, we have come to the end of this study. I hope it was helpful. Thank you very much.
Welcome to Efiwe, excellence without stress.
Welcome guys to Efiwe, excellence without stress, and I remain your favorite chemistry tutor, Godson. We are going to be considering something very interesting today. You know how Ezichi is called Zichi or Z-Baby, and Olorutoba is called Toba. Chukwemeka in the East is called Emi-Boy or Mekus as nicknames. Chemical compounds also have nicknames, and for me, those nicknames are their chemical formulas. So, these chemical formulas are more simple and cooler ways to identify this compound. And because of that, we are going to be considering empirical and molecular formula. Now, generally speaking, there are 3 major ways of representing compounds. Generally speaking, you have your structural formulas, your empirical formula, and your molecular formula. But for this particular study, we are going to be concentrating on the molecular and empirical formula. So, what is an empirical formula? An empirical formula is simply defined as the simplest chemical formula which gives the ratio or proportion of combining elements in one molecule of the compound. So the implication is that the empirical formula will not give you the exact number of elements, but it will tell you a proportion. Proportion simply means, take for instance, I tell you, you have a basket of fruit and there are 30 fruits in that basket. If mango and orange are in a proportion of 1:2, it doesn't mean that there are only 1 mango and 2 oranges. The implication is proportion just gives you a ratio relative ratio of the two things that are combined there. And that is what empirical formula basically does. Now, we are now going to consider the rules to determine empirical formula. The first rule is identify the constituent elements in the compound. So if, for instance, you have a question, and in that question they tell you, given that a particular hydrocarbon, once you hear hydrocarbon, the substance is basically going to be containing just two elements, which are carbon and hydrogen. So the first thing you need to do is to identify the constituent elements. The second thing you need to do is to identify the percentage or mass composition of the constituent elements. Yes, check out for the percentage composition, which is going to be given in the question, or after your analysis it will be given to you. Then you go to divide the percentage or mass compositions by the corresponding relative atomic masses of the elements involved to get what we refer to as the mole ratio of combining elements. So just have that in mind, that the third thing you do is to divide and get your mole ratio. How do you get your mole ratio? You take each of the percentage or mass compositions and divide each of them by their corresponding relative atomic masses, and then you have your mole ratio. Now, this implies that if you have a mole ratio, or if the number of moles of the constituent elements we are already given in the question, you don't need to apply rule 3. Yes, so basically rule 3 is done to find mole ratio, which means if you are given mole ratio directly, automatically you don't need to apply rule 3. Once you are done with application of rule 3, or maybe you already have the mole ratio, you divide all the values of the mole ratio by the smallest value among them. The answer obtained gives the proportion of elements combined, hence its empirical formula. So basically, these are the basic things you need to do, and once you do this, you are done with getting the empirical formula. Now, something that needs to be noted is this: if any of the final values is a 0.5 decimal, multiply all the values in the question by 2. Secondly, if any of the final values is a 0.3 decimal, multiply all the values by 3. So we're going to see questions to help us understand this. So if, for instance, you're done with solving and maybe you had 1.3 and 2, the implication is that you're supposed to multiply everything there by 3. If, for instance, you have 1.5 and maybe like 2, you're supposed to multiply everything there by 2. Basically, that's the rule you get. But you can approximate the other values like 0.8, 0.9, 0.2, 0.1. You can approximate those ones. However, once it's 0.5, 0.3, or 0.6, this is exactly what you're supposed to do. To understand the rules and its application, let's solve this question. An organic compound contains 60% carbon, 13.3% hydrogen, and 26.7% oxygen. Calculate its empirical formula. So please take note of these values as we are going to be using them. So for carbon is 60%, for hydrogen is 13.3, and for oxygen is 26.7. The question now says calculate the empirical formula. For us to do that, let's look at the rules. Rule number 1 says we should identify the elements in the compound. So let's look at the elements in the compound. The elements we have in this compound are carbon, hydrogen, and oxygen. That's the first rule. Rule number 2 says identify the percentage or mass compositions of the constituent elements. So as you can see, the percentage of carbon is 60, that of hydrogen is 13.3, and then that of oxygen is 26.7. So that has been identified. Then we go to dividing by the relative atomic masses to get the mole ratio. The relative atomic mass of carbon is 12, hydrogen is 1, and oxygen is 16. So let's get to solve. Let's go to our board so we can just apply these things and then get our answer. Now, we are going to apply the rules basically as they say. So the first thing we need to do is to highlight or outline the individual elements in the compound, carbon, hydrogen, and oxygen. Then we write out their percentage composition. We have 60 here, 13.3, and then 26.7. Then the third rule says divide each of them by their corresponding atomic masses. So by 12, by 1, and by 16. So let's get to do that. When you do 60 divided by 12, that is supposed to give you 5. When you do 13.3 divided by 1, that's going to give you 13.3. And finally, when you do 26.7 divided by 16, you are going to have 1.669. The next thing you are going to do is to check for the smallest value amongst them and use it to go through all of them. So we have that this is going to be divided by 1.669. This is going to be divided by 1.669. This is going to be divided by 1.669 because that's the smallest value to apply rule 4. And when you do that, 5 divided by 1.669 is going to give you approximately, that's 2.9. 2.99, which is eventually going to give you 3. You know we can approximate if it's 0.9. Then here we have that 13.3 divided by 1.669 is going to give us 7.9, which is approximately 8. We can approximate 0.9 values, and then here is going to be 1. The implication is that our empirical formula for this particular compound is going to be C3H8 and just 1 oxygen. So let's go and check if this is even in the option. So let's look at the options. We have option A, C5H12O. That's not it. And option B is definitely our answer, and that is C3H8O. Moving ahead, let's try some more questions. A hydrocarbon containing 88.9% carbon has the empirical formula of dash. So let's go back to check the rules. Remember what the rule says. First of all, identify the constituent elements. And when you hear hydrocarbon, the implication is that the only elements there are carbon and hydrogen. Then you identify the percentage of mass compositions, just as we are going to do in this question. The percentage of carbon is 88.9. Okay, let's get to solve. So taking this out so that we can use our screen. Okay, I guess we can do that now. So solving, we have that we have carbon and hydrogen as the only elements there, and then carbon has the percentage of 88.9. Now, how do we find the percentage of hydrogen? It's very simple. If you have that total percentage is 100, and that total percentage is carbon plus hydrogen. If carbon is 88.9, hydrogen is going to be equals X. So which means that if you do this, hydrogen or X is now going to be 100 minus 88.9. So if you do that, that is going to give you 11.1. So that's that, basically 11.1 for hydrogen. Now let's continue. We divide by the atomic masses. Quite simple, just follow the rules. You can go back and check out the rules or look at the rules in the note that is going to be put out in the Efiwe app. Remember, if you don't have the Efiwe app, go and get it. So it's 8.9 divided by 12, have 7.4, and then here remains 11.1. Then we use the smallest value, applying rule number 4 to divide all through, and this is going to be divided by 7.4 divided by 7.4. We are going to have 1 here, and here is going to be 1.5. Now if you go back to our slide, we made a point or noted something. If any of the final values is a 0.5 decimal, multiply all the values by 2. So with that said, we are supposed to multiply both values here by 2 because we have a final answer as 0.5. So multiplying, this is going to be 2 and this is going to be 3. Hence, our empirical formula for this question is going to be C2H3. Okay, let's check if that is in the option. So moving ahead, and yes, that is option C, and that's correct. I presume this is quite simple to understand. Now, let's try out a question that has to do with moles. The empirical formula of a hydrocarbon. Remember that once we say hydrocarbon, the implication is that it contains only carbon and hydrogen. Contains 0.12 moles of carbon and 0.36 moles of hydrogen. In this question, you are given the moles, which means you don't need to apply principle number 3. Let's check this out. So solving, this is going to be quite simple. Take this out. Hydrocarbon implies carbon and hydrogen. And then you have that the carbon is 0.12 moles, while this is 0.36. Because it's already in moles, it's already the mole ratio. So we are already in step 3, which means the next thing you need to do is step 4, which is dividing both sides by the smallest value among them. Dividing both sides, this is going to give you 1, and this is going to give you 3. Hence, the empirical formula is going to be equals CH3. Okay, the next thing we are going to now talk about is molecular formula. Now, molecular formula is the simplest chemical formula which indicates the exact number of elements combined in one molecule of a compound. The molecular formula is related to the empirical formula by the expression molecular formula equals empirical formula times n, where n is usually a whole number value which multiplies the subscript of the empirical formula to give the molecular formula. So once you're asked to find the molecular formula, all you need to do is find your empirical formula, then find your N, then multiply the both of them as you have seen, and you get your answer. Now the question is this: how do we find N? Finding N is quite simple. N is simply given as the molar mass of the molecular formula divided by the empirical formula. In most cases, you'll be given that molar mass. But then how do you find the empirical formula mass? So let's look at this. From what we solved in the last question, if you have that this is the empirical formula, to get the mass of the empirical formula simply means that you need to add carbon plus hydrogen. There are 3 of them, so times 3. So let's get to add them. Carbon's mass is 12. That of hydrogen is 1 times 3. And then this is going to be 12 plus 3. And this would give us 15. So if you are asked to find the empirical mass or the mass of the empirical formula, simply add the atomic masses and you will get the mass of the empirical formula. On the other hand, you are likely going to be given the molar mass of your molecular formula, basically. Now, in a situation where you are not given the molar mass, you can be given the vapor density. Now, if you are given the vapor density, relative molecular mass is equals vapor density times 2. Hence, the implication is that in place of the molar mass or relative molecular mass, what you can put there is vapor density times 2. That's why our new formula will now be equals N equals vapor density times 2, because we are just replacing, instead of writing molar mass over empirical mass, you simply put the vapor density times 2 and you get your answer. So just have this in mind, that molar mass is equals vapor density times 2. So if I have a question and tell you that the vapor density is 2, what is the molar mass? It's 4. If the vapor density is 6, what's the molar mass? It's 12. If the vapor density is 13, what's the molar mass? It's 26. So just have that in mind, that once you are given vapor density in the question instead of molar mass, what you simply need to do is to multiply that vapor density times 2 and you have your molar mass value. Okay, so going back again, how do you find N? Molar mass of the molecular formula divided by the mass of its empirical mass. Okay, now other conditions or situations that can occur is when you are given mass and volume and expected to find molar mass. How do you do it? If mass over molar mass is equals volume in DMQ or 22.4, the implication is that if you make molar mass the subject of formula, you can actually try it. Molar mass would now be given as mass times 22.4 all over volume in DMQ. On the other hand, if it's in cm cube, it would be molar mass equals mass times 22400 all over volume in cm cube. So I'm giving you different scenarios where you might not be given the molar mass directly and you are expected to find it. So you find out that our N value will now be mass times 22400 over volume in cm cube times 1 over empirical mass. And that's that basically. So we are going to be trying out questions to help us buttress and understand this particular concept. So you have this question first. The question says 56 cm cube of a gas at STP weighed 0.11 gram. What is the vapor density of the gas? Okay, so this is going to be quite simple to do. And how do we resolve this? When you are asked to find the vapor density of a gas, vapor density, as you know, is given as, let's take all this out so we won't get confused. Vapor density, as you know, is equals the molar mass or relative molecular mass divided by 2. That's why we said that molar mass is equals vapor density times 2. So if you make vapor density subject of formula, you get this. Now from this question, if you look at it, you will notice that we were not given the molar mass. However, we were given the volume in cm cube and the mass. Now, if you go back, you will notice that there's a way to relate molar mass to volume in cm cube. And how do you relate molar mass to volume in cm cube? Molar mass is equals mass times 22400 divided by the volume in cm cube. And that is exactly what we're going to use to find the molar mass. When you now get your molar mass, you now put it in your formula and get your vapor density. So let's get to work. So the molar mass is equals mass times 22,400 divided by volume in cm cube. So the volume in this question is given as 56 cm cube, while the mass is given as 0.11 gram. So let's put this into the formula to find the molar mass first. Then we now use the molar mass to find the vapor density. So to find that, as we said, the molar mass is equals mass times 22,400 divided by volume in cm cube. So if you do that, the molar mass is going to be equals what? Now let's look up our values. The mass given in the question is 0.11, while the volume is 56. So let's get to that. 0.11 gram multiplied by 22,400 all divided by 56. So let's do this. If you have this, you are supposed to have 44 gram per mole as the molar mass. Now, if you are asked to find the vapor density is equals molar mass divided by 2. So if you put the molar mass which we got as 44, dividing it by 2, our answer for vapor density would now be what? 22. And that's that basically. So with this said, let's check if our answer is even in the option. Okay, so that is going to imply, let's look at that. Yes, and that is our answer, option B. Okay, so let's try out more questions to help us understand how to find molecular formula. A hydrocarbon with an empirical formula CH and its vapor density is 39. Determine its molecular formula. So let's look at how to find molecular formula originally. According to the questions, when you are asked to find molecular formula, what you need to do is multiply the empirical formula by n. The question is, how do we get n? Molar mass of molecular formula divided by empirical formula. But if you look at this question, we were not given the molar mass. What we are given was the vapor density. So what do we do with vapor density? So we'll make it the molar mass. If you look back, you will notice that the molar mass or relative molecular mass is equals vapor density times 2. And that is what we are going to do. So we'll convert this particular vapor density to molar mass by multiplying it by 2. So let's get to work. CH is the empirical formula. 39 is the vapor density. And if 39 is the vapor density, it means that the molar mass is going to be 39 multiplied by 2. And that is going to give us 78. With this now, we can get to work. Remember that molecular formula is equals empirical formula all multiplied by n. Now let's get to it. So the molecular formula is going to be equals CH multiplied by n. But we don't know what n is, so let's find n. Now n is equals molar mass divided by empirical mass. We have found the molar mass. So n is going to be equals molar mass, which is 78, divided by the empirical mass. Empirical mass, let's find that. That's going to be C plus H. And n would now be equals 78 divided by C is 12 plus H, which is 1. And that is going to be 78 divided by 13. So if we do 78 divided by 13, we are going to have our n as equals 6. With this said, you will now notice this, that if we put this in this value, the molecular formula is now going to be CH all multiplied by 6, and you are going to be multiplying that subscript, not the compound entirely. So that's going to be MF equals 6 times the 1 here is going to be C6, while 6 times the 1 here is going to be H6. And that's basically that. Let's check if that is even in the option. So looking through the options, let's see what we have. And that is going to be option D, and that is the correct answer. So you will notice this, that if you do not find the molecular formula, you will not get the exact number of elements that is found inside that particular compound. So the last question we are going to be considering for this particular study is this, and what does it say? The molar ratio of carbon to hydrogen of a volatile liquid compound is 1:2. Now let me say this. Once you are given a mole ratio and it is reduced to the lowest possible term, that is going to be equivalent to the empirical formula. So we can say that the empirical formula for this particular question, empirical formula, is equals 1:2 of carbon, which means 1 of carbon is to 2 of hydrogen. It's already reduced to the lowest term. So even if we decide to solve with the principles of empirical formula, this is eventually what we are going to get. Now, moving ahead, you now have that they now said 0.12 gram of the liquid on evaporation at STP gave 32 cm³ of the vapor. The molecular formula of the liquid is dash. Now we already know how to find molecular formula and know that we need n. And to find n, you need molar mass. But you are not giving molar mass in this question. What you are giving was mass and volume. I already showed us that we can actually find the molar mass when you are giving mass and volume. How do you get it? Molar mass is equals mass times 22,400 divided by volume in cm³. And that is exactly what we are going to be doing in this question. So let's get to it. So to find the molar mass, we are going to have this equals mass times 22,400 divided by volume in cm cube, and that is going to be molar mass equals the mass given is 0.12 multiplied by 22,400 all divided by 32, and that is going to give us divided by 32, that is going to give us 84. So you have that the molar mass of this particular substance is 84. Now that we know that this is 84, what are we going to do to find the molecular formula? Molecular formula, as we know, is empirical formula multiplied by n, which means the molecular formula for this liquid is going to be CH2 multiplied by n. How do we find our n? N is equals molar mass divided by empirical mass. We have already gotten the molar mass, and that is 84 divided by the empirical mass. Sorry, this is supposed to be empirical mass. Let's get to the empirical mass. Empirical mass, we have C plus H times 2. And if you do that, this is going to be 84 divided by C, which is 12, plus H, which is 1 times 2. And that is going to give us 84 divided by 14. Now, when you have 84 divided by 14, you are going to have 6 as your answer. So what does this imply? It now means that if we are asked to find the molecular formula, which is equals empirical formula times n, the empirical formula that we have in this question is CH2, and then we are going to be multiplying it by the n that we've gotten, which is 6. Therefore, the molecular formula is going to be, remember, you're multiplying by their subscript, so 6 times 1 of the subscript, that's carbon subscript, which is C6, and then 6 times 2, and this is going to be H12. So basically this is our answer. Let's see if it is even in the option. So taking that there, we are going to have let's bring up back our slide. So yes, and that is basically option D. I presume that this video has been helpful in your understanding of empirical and molecular formula.